Now today we will start talking about Gauss law, and which is one of the most important topics in electric field calculations. We'll first start by defining an important quantity which is vital for the introduction and understanding of Gauss law, which is the electric flux of the electric field through some surface. Now before that, let me just outline what is Gauss law useful for when it comes to calculating the electric field. Gauss law provides, for our purpose, it provides an alternative tool, an alternative method to calculating the electric field. And we have Gauss law because the electric force has an inverse square law behavior. In other words, because as you have seen in the electric field or in the Coulomb's law, the force between two charges drops like 1 over r square. Now, it is because of this 1 over r square behavior that we have Gauss law. We might talk about this more when it comes to when we introduce Gauss law later. Now, Gauss law is useful for calculating the electric field mainly of continuous charge distributions, which we have seen that you need to integrate in order to find that electric field, only when you have high degree of symmetry. So if this charge distribution has a high degree of symmetry, then Gauss law becomes a very convenient, technically easy way to calculate the electric field. And it is important to understand the properties of many materials, like, for example, conductors, electrostatic equilibrium. Gauss law, this is vital in understanding these properties. So let's start with the electric flux. Now, here we will assume that I have a uniform electric field. So as you can see, the field lines are straight lines, they are parallel, and they are equidistant. Therefore, this is a uniform electric field. Okay? Now imagine that you have a surface here that is cutting these electric field lines perpendicular to these lines. Okay? This surface need not be a real surface, by the way. You can think of it as an imaginary surface, or it might be a real surface. It doesn't matter. Okay? So you have this surface. Now, the quantity of interest for us now is the electric flux. The electric flux of the electric field through this surface is defined as the product of the magnitude of the electric field at the surface multiplied by the surface area perpendicular to these lines. Okay? So it's a product between two quantities, E, which is the magnitude of the electric field at the surface. In this case, it is the same everywhere because the field is uniform, but generally the field might not be uniform. So the flux is in general the product of the magnitude of the electric field at the surface multiplied by the area that is perpendicular in a plane perpendicular to the field lines. Okay, this is the definition of the flux. It is the product of two scalar quantities. Modulus E is a scalar quantity. Area, in this case, is a scalar quantity. So it's a scalar. The flux is a scalar, and it has units of Newton per Coulomb meter square. It doesn't have a special name. Unlike the magnetic flux that we will discuss later, we will see that it has a different name. But here we don't assign it a different name. It is just Newton per Coulomb, the electric field unit multiplied by a meter square, which is the area. So this is the flux. Now, what if the surface was not perpendicular that you want to find the flux through, the surface that you want to find the flux through was not perpendicular to the field? In this case, how you find the flux through that surface? Well, in this case, you find the area of the surface projected into a plane perpendicular to the field. Okay? So this is the area that you want to find the flux through it. You project it into a plane that is perpendicular to the field. This is the plane perpendicular to the field, as you can see, and this is the area. Part of it is shown. This is the part of the area that is projected. This is the area that is projected to the plane and onto the plane that is perpendicular to the field lines. Now, how we do this projection? We define here the normal. This normal, when you talk about a planar area, is a vector, is a line or a vector, if you can think of it, that is normal to the surface. Now, when the surface is a plane, it is the same all over, everywhere. I mean, if you carry the normal that you draw here is the same as here, 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 wherever is that. Okay. So this is the normal. Now, theta here is the angle between the electric field line and the this normal. Now, for a planar surface, a uniform electric field, this is the same for all at all points. Now, this theta, which is the angle between the uniform electric field and the lines and the normal, is also this theta, okay, geometrically, and therefore the projection here is A perpendicular A cosine theta. Now, this quantity is in general smaller than the area, as you expect. When you project the area into a plane perpendicular to the field, of course, it becomes smaller, as you can expect. And cosine theta also is quantity which is less than 1, and so this is smaller. So in this case, this is what you do. And in this case, you define this A perpendicular, and the flux becomes E multiplied by A perpendicular, which is E multiplied by A cosine theta. Okay? So that is your flux when you have the electric field lines not perpendicular, the electric field line, the surface not normal to the electric field lines. Now, we can think of the electric flux as actually being proportional to the number of electric field lines crossing a surface. Now, this should make sense because we know that the electric field, the magnitude of the electric field in some region is, as we have defined that when we introduce the idea of electric field lines, that the density of lines, which is the number of lines that cross a surface perpendicular to that surface, this number of line is proportional to the electric field. So when you have larger electric fields, you will have more lines. And since the flux is the product of electric field minus area for two surfaces, if you have two identical surfaces and two electric fields, if you have a stronger electric field on one surface perpendicular to it, then the flux through that surface will be more than the flux in the surface which has weaker electric field. But stronger electric field means larger number of lines crossing that surface. And therefore, larger flux will correspond also to larger number of lines crossing the surface. And so we can think of the flux as being in terms of the number of field lines crossing a given surface because of the relation between the electric field line density and the strength of the electric field that we have introduced when we defined how to draw electric field lines. Now, this view, this picture actually is quite intuitive, and it is welcomed because the term flux refers to something that is flowing. You know, we talk about the flux of water, for example, or in a pipe or in a river and so on. So here, when you have electric field lines, these arrows, somehow they resemble a flow of something, and so it makes it intuitive to think of the flux in terms of these electric field lines. Although formally, the flux is the product of the magnitude of the electric field multiplied by the area that is perpendicular to the electric field. Now, evidently, from this formula, for a given E and for a given surface, the flux can be positive if cosine theta is positive, can be 0 if cosine theta is 0, in this case theta equals pi over 2, and can be negative if cosine theta is negative. Now, cosine theta is negative if the angle between E and the normal is between pi over 2 and pi, and it is positive but when the angle is between this theta is between 0 and pi, and it is 0 when the electric field is perpendicular. The surface is the electric field is parallel to the surface or perpendicular to the normal. Okay, perpendicular to the normal means parallel to the surface, and in this case theta will be equal to 0, and you will have 0 flux. Well, you can understand this also intuitively because the field lines now are moving tangent to the surface. They are not penetrating the surface when they are normal to the surface. Now, this expression that we have derived for the electric field lines, this is valid if your field is uniform over the surface and if the surface doesn't have a curvature, because only then you can define a single A and a single cosine theta over that surface. If the field varies over the surface, then you cannot define a single E. If the surface has a curvature, okay, then in this case the cosine theta, the normal, will not be the same at all points in the surface. Okay, therefore you cannot use this expression to find the flux. But come on, there is a field, and this field line, there are field lines, and these are field lines flowing through that surface. Even if that surface is not, even if the field is not uniform, or the surface is not just a plane. So how can we calculate that flux? Well, evidently there is a way to do that, but first do this checkpoint, and then we will see how we can calculate this. Yes, so consider this surface. This is an arbitrary surface, can be curved. It's an open surface, it can be curved, it can have a curvature, completely arbitrary. And it is an electric field. The electric field is not uniform in space, and it's not uniform on the surface. Okay, so it has different magnitude and directions on different points on the surface. Now, and I want to find now what is the electric flux through this surface. What I do in this case, well, the idea, which we are familiar with probably now, is you assume that this surface is composed of small elements, area elements delta AI. So divide the whole surface into small area elements delta AI. I'm showing only one of them, but you have to imagine that this whole surface is divided into small area elements delta AI. Now, these are small. How small? Well, as small as you can. And also, they are small so that the electric field does not vary a lot and is approximately constant over this area. This is number one. Number two, you make this area, you define a vector, which is delta AI vector, you can see here. Okay? And this vector has a magnitude equal to this area element, but its direction is normal to this area element. Okay, so this is the delta A vector, delta AI vector, okay, or the area element vector. This is another vector. Now theta I here for the ith delta AI is the angle between EI and delta AI. Now for each of these delta AIs, now I'm taking here the ith one, E is uniform. This is almost a plane because when it's small enough, even if you have curvature, it is like a plane. So it's almost a plane, okay? And therefore, I can apply this formula that I have defined earlier for a uniform electric field and a planar surface to find the flux element, I call it now. Why element? Because it's a delta. It's the flux through the area element, not of the surface, not through the whole surface. I define it using this expression, which is EI delta AI cosine theta. Now I write this as a dot product, EI dot delta AI. You remember the dot product of two vectors, modulus the first, modulus the second, cosine the angle between them, and this is exactly what you get. So now I can find the flux through this ith area element, and which means I can find the flux through each actually area element that covers the whole surface. For each area element, you will have a different EI, you will have a general a different theta I. Okay. Now, to find the flux through the whole surface, you sum all these flux elements, delta phi i's. And this summation goes from 1 to n. Now, okay, in the limit, when delta AI goes to 0, when you make these, shrink them to 0, okay, in other words, you make their number infinite, then in this case, this becomes exactly the flux. And in this case, this limit, which is reminiscent probably of Riemann sum in calculus, and this reduces to an integral. So the flux now is given by this integral, which is this integral. Understand it as the limit of this summation when delta AI, when the area goes to 0. So this is how you write it down, and I put surface here just to remind you that this is a sum of an integral over surface. So this is the flux through any surface. This is the electric flux through any surface, by any electric field penetrating that surface. This is the most general expression for the electric flux through any surface. Okay. Now, this integral is known in calculus, of course. No, it's an area integral. Even if you have not taken calculus at that level, this is not a problem. Just you need to understand that this integral means this. Actually, it's the sum of the flux through each area element when the area of this area element becomes 0. Thinking of it this way will just make you comfortable with this expression. So, okay, so think of this integral as just telling you, do this summation, okay, and you will be comfortable with that form of integral, which might still be not familiar to you at this level, but definitely it is not a problem. It is not a problem. Now, evidently, the value of the flux through a surface will depend on the shape of the surface and also on the electric field on the surface. So it depends upon two things. Now, this is a good checkpoint that you should do carefully before you proceed.